If I have time, I sometimes give some talk. Now it's the time to collect everything together and try to get an overview for what we have done. So basically what we are trying to focus is this one is the vertical structure. I think I have to change it because this is only a 10-minute talk. I think I downloaded a long one. Hold on a second. This talk, I gave this talk in CloudSet Science Team meeting just last week, so get some confused. Sorry about the delay. Oh, shit. No. Okay, so the time, try to reload the correct one might be a difficult time. So I will try to give my best, to give this talk. In general, I try to give an overall review, but right now I can only focus on the vertical heating, radiated heating. That is the major focus from this course. So, Okay. All right. So we're going to focus on the vertical heating, radiated heating structure, and their impacts on the water vapor, and the low-level winds, and radiation. So there's a bias related to the very specific model setup. So when we design the clouds and their radiation folding, sometimes depending on the past computer limitation, so we cannot do really high resolution and also consider too much detail and too realistic setting. It's not to say that in the past time, the scientists, they did not know how to implement the good and the proper cloud radiation effects in the model. Okay, there's so many limitations and realistic consideration. So it is a time for us to consider more about how to put back, that scientists already knew in the past research. So I'm going to focus more on the new data set. We call it YASI MJO Task Force. So we use the 21 related model. That is the model that particularly generate for the MJO study. So the CME 3 and CME 5 model data, they do not have the radiated heating. So they cannot really use for us to study the vertical structure. So the MJO Task Force, they do offer some very detailed daily heating rate for 20 years. So we can take advantage for this model, and therefore we can study how the model under the cloud radiation bias circumstance, how the impact from the circulation and the energy budget. So we use the NASA trained observation from CloudSat and also the radiation from Cirrus and Calypso. So we do have a combined data set for cloud, water, and the radiation. Okay. And airs, we can use the airs for our water vapor and the land surface temperature study near surface, but I'm going to show you here anyway. Okay, so the representation of the cloud water that in the current GCM, imagine this is real world, okay? So we do have a convective core cloud, and we have floating particle, and we have a floating or suspended particle, ice particle, and the suspended liquid and the floating rain. So this is a real world, the hydrometeors wise, we do hope that model can carry this hydrometeors properly. And however, because some background I just mentioned, that in the past the computer resource were limited, and there was no needed then because Quebec is so big. So at this point, most of the current advanced GCM, they carry the floating ice, that is the envelope of stratiform ice. They do not prognose, that is, keep the falling snow with memory or history, That is to say, when the model compute the next time step, they will start it from zero. The gray box do not have falling particle information. And the same thing to the falling rain. Okay, those two are very critical, and I hope everybody keep in mind in the following presentation. And the other important thing is convective core of mass. They only about 6 to 8 GCMs currently, they do consider convective mass and the radiation interaction. So 90% of the current GCM they do not consider. So you can imagine this is what the model we're going to interact with the radiation. So our research is starting from here, and this is the total ice water pass. And the total ice water pass against the CloudSat and Calypso ice water pass difference. So on your left is the CME 3. So this is a multi-model mean that we have about 20-something couple GCM ice water pass minus the CloudSat climatology. And this is the CME 5. So as you can see, over the tropical regime, IPCZ and the ITCZ regime, you do see there's a significant underestimate of total ice water pass. So that is to say, the cloud will not going to shed much solar radiation, opaquely to stop the long-wave radiation emitted out of the space. So imagine this is real world. So we do have an incident and the short-wave downward radiation, and this is a reflected short-wave radiation at the top. And this is the long-wave emission at the top. So these two are going to give you an imbalance. That is to say, if the model do not really consider some thicker, optically thicker cloud, then you will tend to have too much long-wave emission escape away to the outer space. And similarly, so because cloud is not thick enough optically, so the short wave are going to reach at the surface much more than the reality. So that you have too much out and too much in. So we have too little out. So any global model exercise, if one of you are global modeler, you want off to see if your global model energy is balanced or not at the top of atmosphere. That is to say how much in, how much is reflected, and the long emission. If you take the long-term average globally, the system should be balanced. That is our, at least a requirement. We need to, get some requirement to. And below the top of atmosphere, then people, as a modeler, they will consider the cloud fraction, effective radius, and the cloud mass, and of optical depth, things like that. Those parameters that we need to tune, quote, or adjust based upon or constrained by the satellite data. So that's what our group is doing. So we first check the model type if they indeed are balanced. That is to say the out and the in, this is a balance in a global sense. Then we're going to study what happened in the troposphere. So we expected to have the underestimate and overestimate short wave and overestimate or outgoing long wave radiation. Okay, so we published a paper along the line. So we published a paper to report what we found from the ice water content in the global climate model community that we do have an underestimate. Then we found that from for example, outgoing long radiation. So this is an 8 m5 round that is prescribed SST. And over the SPCZ and the ITCZ, we do see some very, I forgot to put the color scale here, about 10 to 15 watt-meter per square. So you can see there's no double ITCZ because constrained by the prescribed SST. And this is a couple semi-5 round. So the ORR and the outgoing long radiation, when we try to use the semi-3 or semi-5 to study the vertical radiated heating structure, because they do not have the data, so we using the MJL task force. So we use radiated heating profile output from the YASI MJL task force. So we use a 20 years prison climate simulation. Try to be clean, so we only use the AMIP run. So they do have 3 model have a couple run, but we only use the AMIP run. Then we're going to use the data against our NASA-derived radiated heating profiles, which is a 2D FLXR LiDAR. So the idea is probably one of the 2 data sets available to have a chance to look at and examine the model of radiated heating. One is the CCCM, the other one is that is Lenny, and the other one is from the CloudSat science team, Tristan's data. So we're going to use this in order to indirectly to verify the semi-3 and semi-5 model, the dynamic or water vapor bias, to see if this is related to what we are facing. Okay, so this is a cloud set. I think this is a cloud set long wave radiated. So this is the total long wave heating rate that we have 4 years in the climatology. So this is a precipitating profile that we collect if the condition is precipitating, the long wave heating rate, and this is a convective long wave heating rate. So one can see that convective form of latent heating contribution in that pixel cannot be really ignored. And this is a precipitating. So most of them are stone track, and little are from the convective core. So stratiform from the precipitating stratiform part contribute most of the total long wave cooling rate. And this is the precipitating or convective. So the story behind this decomposition is because earlier we just mentioned the model do not carry the prognosis, the falling particle and the convective mass of the long wave heating, such that this two has to be studied. And what data set we should use is the total long wave heating rate, or is we remove those contributions because model do not have that mass to interact with the radiation. So like we did before in our ice water content paper, that we basically remove or filter out any cloud set calypso retrieval whenever there's a precipitating condition or convective condition. And we call it non-precipitating and the convective condition. And we found that the cloud ice vertical distribution and the ice water paths are matched pretty well because that is because apples to apple, right? So if you're using total, then you got underestimate. So same thing, we found that the total long wave cooling rate that can be reduced by this amount, and we suggest that this is the one you can check your model long wave cooling rate computation is right or wrong. It's good or not. But in real world, we should use this to study how the model should respond if there's a bias due to lack of the falling rain particle contribution and the convective core mass contribution. Okay? All right, this is the show wave radiation, heating rate. So show wave heating rate, something we have some assumption from the show wave, from the convection, and this is from the falling particle. So combined, we remove this from here, and we got this. So there's about 20 to 30% in general that the heating rate is reduced based upon our very ad hoc method as a first look to see what exactly the model performance is. All right. So we already presented that the OLR, that model does have a bias, has too much outgoing long wave radiation out, in particular over the SPCZ and the ITCZ. So the semi-far, and this is the YACI, we use 21 model results. It's the multi-model mean outgoing long wave radiation. So not surprising, these two should be similar because most of the YACI contribute models are contributing to the AMID and the CMID. So in terms of the AMID run, they should look similar. Even you can see the pattern and some detail are very, very close. All right, so next step, we would like to see what is the vertical heating bias from this YACI multi-model. So we took the regime from now on, I'm going to show the multi-model mean result against the cloud set and Calypso radiated derived data. So we focus on the tropics, that is to say 30 to 30, and we take the zonal average and to see what is the bias looks. And we slice at 500 hectoscale. So this is the long-wave cooling rate that the bias against the unfiltered, that means its total heating rate, the observation. On your right is we use the filter observation data. So from your right, you can see that over the Pacific section, the bias is much less than if you're using the unfiltered, that is the total radiated heating rate data. So it's good. It's good to us to see that the bias are really small, meaning our global climate model are doing good job in their long-wave cooling computation. See, it is very close to what the retrieval shows. So this is good. But now we're going to bias you that, our model is doing a good job. However, we should look at the reality, realistic world, real world. So we should check this one, not this one. So we do have a bias somehow. And the bias is located over the SPCC, IPCC, something that we did mention earlier. The bias located over heavily rainfall regime that have more falling rain and a convective mass regime. So, by doing that, we would like to see the Pacific Basin, try to avoid the continental regime because there are too many details from the land surface process that can complicate our study. So we like to see over the ocean to see what the ocean, more simple way. Okay, so this is the long-wave heating rate bias multi-model mean against our observation. So south to city nodes over the Pacific Basin. So one can see that there's a clear too warm, that is less cooling bias, and the too cold bias. And this is response to the convergence from the cloud top to the space. And this is what we just mentioned, that the long-wave cooling, that is long-wave escape too much because cloud is too thin, such that they cool much at the top, and warm rather near the boundary layer. And this is very difficult to argue because the cloud set has some issue about the cloud liquid water content retrieval. So sometimes we need to use other data set that may not have the liquid raining information considered. So we can assume that rainwater might not be that important as application-wise to the radiation. So it might be okay to make some big assumption there. However, for the ice part, so we can focus more on this part rather than over the lower part. So we do see some warming and cooling, less cooling, too strong cooling, less cooling structure over the Pacific Basin. And this is a warming, so this is a short-wave bias. A short-wave bias has much less impact difference bias than the long wave. So we're going to focus on the long wave only. Okay. Okay, so we would like to see this profile, this regime, the regional profile. Okay, so this is the regional profile. So this is short-wave bias, and this is a long-wave bias. So one can see when we use that ITCC profile from the multi-model mean, we find that the long wave tend to give you upper level cooling. That is cooling too much. And there is some warming that is less cooling, or maybe even warming effect. And then this tilting give us this kind of tendency that is too much. So there's a vertical unstable structure. So that is to say you have too much cooling. So this whole ITCZ will be unstable based upon this. And we do see that condensational latent heat, we're going to compensate this long wave bias. So we do see there's a condensational heating. That is to say you're going to have excessive rising motion. That is, the convection will become too strong. So we have excessive upward motion, and we're going to build up a local subsidence. Okay? So vertically, there's a destabilizing radiative heating, basically from the long wave part over the heavy precipitation regime. That is IPCC and SPCC. And this is going to trigger the compensation thick convective activity that has a stronger condensational heating. Okay, this is some cartoon and animation cartoon only. So this is one pole, ITCZ, SPCZ. So along this ITCZ, you have long wave bias we show in the very two slides. And we have a short wave too much absorption bias. So this will give us the radiative heating unstable, and we're going to have an excessive updraft ascending motion. And when we reach the top atmosphere or reach at the cloud tower layers, they're going to spread out, and they're going to come across and have a convergence, and there's a subsidence will generate some low-level flow convergence. So we report this in our two papers, and the impact for this effective convergence due to this effect. Okay, let me try it again. It's very difficult to to understand at the very beginning. So you have a long way too much out, short way too much in, and you build up an unstable layer. And we found that from our multi-model mean of vertical radiative heating and cooling, we found has a compensating the updraft, and therefore you have a divergent and become a low-level convergence. You put up a convergent flow here, and this low-level flow, we're going to bring you some water vapor. That is to say, we transport some warmer and humid air in here, and they do have a convergence, and you have too much water vapor over the terrain boundary layer. And this too much water vapor will going to give you clear sky, long radiation, and short radiation bias. So we reported in our recent papers. In the meantime, we would like to see if this is also shows in YASI MGL task force. So we do see for the 850 millibar heat pascal, we do see that multi-model mean give us the bias against the European Center entrance data. So we do have a convergent flow like this. Very similar to what we found in the CME3 and the CME5 papers. And same thing to this direction, okay? All right, so this is the multi-model mean water vapor bias against AIRS, NASA AIRS water vapor data. And we can see the same thing when we compare against the CME3 and CME5 we reported. That is to say, we do have a convergence from ITCC, SPCC, so we're putting the warmer air into the terrain boundary layer, where the regime is supposed to have a cold advection and should be drier, but because of that cloud radiation bias, we generate a low level, we call it effective warm and moist advection that should have been in a drier and cold environment column in the terrain boundary layer, terrain subsidence regime becomes a little bit too warm and too humid. And this is going to trigger some deconvection activity. So this bias is confirmed not only from our CME3 and CME5 result, but also from this very detailed vertical structure, daily vertical structure. And this is a precipitation bias we found. So same thing. So we do have, this should be correlated. And so we have some, so this will maybe contribute a little bit double ITCC. But we are not claiming this is the reason for the double ITCC, but should be associated with double ITCC, okay? All right, so this is CME5, just for comparison that the 500 hectoscale and this is 500 hectoscale from the Yasi round. So this is an absolute difference. This is relative to the air. So you can see that subsidence regime, subsidence regime, subsidence regime, subsidence regime, that we have too moist and this is too dry. So they kind of perform the same thing even from the couple round. So it's nothing to do with the couple or uncouple. So no matter you are couple or uncouple, it's not the reason for making the difference. It is because the more atmosphere side. However, this could give you some excessive forcing to the ocean surface wind stress. So, so the conclusion from this very interesting short talk is so the vertical destabilization of heating profile that associated with the ORR and the downward show wave are identified. Okay, and it is conjunctions with the low-level effective convergence over the trailing regime. So this will going to increase the column of moisture and the precipitation over this regime. So this is probably very important for even the clear sky radiation, like I mentioned. So combine Calypso and CloudSat and other A-train data, that those data are very useful for our understanding. So what we propose to saying that we would like to suggest that rather than look at a local and one parameter, we probably can take advantage from the space. There are a lot of satellites. So many satellites can give you so many very important information depending how you use them. For example, you can use the water vapor from airs. You can use the modest SST. You can use the CloudSat, Calypso, derived heating rate, cloud fractions, etc., etc. And they are looking at the same system. Then you try to realize what happened, why they converge together. Then you can go back to see why the model has this bias, that you have good reference and can pick it up. I know there's a range of uncertainty from observation, but if you try to use more data and try to consider some very important particular regime, like Chalet just mentioned about that far IR issue, keep those in mind, then we can get some clear direction in your future study. So, I'm sorry, just try to show you that this is a long road. We start this from way back to year 2007 and 2008, and we figure out the clouds that give us the ice water content is well underestimated. I did not know what happened then, to be honest. Then we figure out that, that is because the representation of ice water content and the liquid water content in the model has big issue. Then, if you consider those weaknesses, that weakness is going to bring you the issue and bias over the radiation. If radiation vertical structure got some problem, then the dynamics should be should have some impact. Then next one will be the ocean SST. So I did not show it here. It should be shown in somewhere that I plan to. So the warm SST bias and cold SST bias got better if you consider the falling snow effect into the model. So hope next time in AGU or AMS I can show you then, all right? But here, I think most of the people here, they listened to my talk before already. So maybe this is good, to show some new stuff here. That is, I didn't show the radiative heating bias. So then we go to the cloud radiation and we improve the European Center by put the prognostic snow and prognostic liquid into their model. And we have water vapor improvement and SST paper we got review just back. So I think I will, maybe lunchtime is here. I will just stop here and taking question. And Sorry about I didn't prepare well for the right PowerPoint. Maybe this is good because time is short for our stomach. Thank you.
I have a short question because if we refer to CSM1, it has a very serious WITCC problem. So it kind of suggests that by considering the radiative effect of falling snow, it can improve that. But in fact, actually, through the coupling, it makes WITCC even worse. So is that really the answer?
Okay, the WITCC is a very difficult question. As the I review a lot of articles and I talk to many colleagues. There are some non-local impact also can contribute that. For example, from the Southern Ocean, I believe that could be a big contribution. For the bias I mentioned here, I think they may have 50%, something like that, not all of them. Our sensitivity study with Wei Liang Li, I think they indeed have some indication because of that moisture will bring up complex of parameterization interaction in the model. So we are trying to figure that out, if that is the case. But I don't think it is a good answer that this will going to contribute or not for the WITCC, because ocean vertical mixing also plays some role in it.
Yeah, I just wonder if you have a, let me ask it a different way. Okay, you use the YODC and the plus G GA, the results, okay, and then calculate the profile, vertical profile, radiation. Then another case, on the other hand, you add the precipitating snow and also do the calculation again, okay, and compare these two.
No. We didn't do that. We just used their model output.
Yeah.
And their model, they do not put the falling particle in their radiation calculation. We didn't do anything. We just used the classic Calypso derived radiated heating rate as a reference and take the difference. We didn't do any sensitivity test from this talk.
But when you say the effect of falling snow,
Mm-hmm.
then how do you know which one is?
I cannot say from this talk, but we do see the difference, and I'm supposed to show the sensitivity test in this talk, but I didn't show, so I cannot say. But indeed, when we include the cloud snow, with or without, with cloud snow, the radiated bias, radiated rate cooling bias is less than
Are there any simulations?
Yeah.
Simulations?
Yeah, I do.
With the falling snow included?
Yeah, we do, but I did not show it here.
Okay.
Yeah, but I can show you later or sometimes. It showed like a 25 to 30% of improvement with cloud snow inclusion. Yeah.
So then I think we can start here. Let's thank Frank again.